Now, hello guys, welcome to this tutorials. This bunch of tutorials that we have is centered around one idea, now which is the recap of probability theory. Now, I prefer to emphasize it is a recap. Now, we will be going ahead with couple of important definitions that are needed and couple of properties that will be needed for us throughout this course, and then we will be seeing couple of very interesting examples. In addition to that, wherever needed, we will be taking use of help of the code to understand and reinforce our ideas of probability. So, without any further delay, so let us jump into that. In the sections that were taught by the professor, he has already introduced the ideas of sample space and the needed things like event space, probability measure and stuff. I will just go ahead with the same recap once for the sake of completeness, and then we shall proceed. That is the plan. So, the first thing is now you should be comfortable with the idea of random experiment. Okay. Now, we perform these random experiments, the outcomes of random experiments we put them, and then that is what we are saying it as the sample space. So, which is represented by this omega which is there, and then it has the outcome of the random experiments. Okay. So, now and then we define what is known as an event. So, an event space is a subset of this omega which is there and set of all possible events that are there, which is represented by this scripted f which is there, which is known as the event space. Now, this will be a subset of the power set of the omega. Okay. So, now for all practical purposes, so during our discussion, now we will be considering this event space to be the power set. Okay. Now, this means that every subset of omega which is there is an event that we have, and then we have the idea of probability. See, probability is a function, okay, that assigns a number between 0 and 1 to each of the event, and it has to satisfy certain properties, and these are what are famously known as the axioms of probability. Now, we use this scripted p to represent the probability. Now, this probability is a function from the event space which is this f to this real r, and it has to be satisfying these following rules. Now, the one is the non-negativity. Now, that means that probability of any event which is there will be greater than or equal to 0. Now, you cannot have any event whose probability is a negative value, okay, that is not possible. Okay. So, and this is for all the events as I told you, and then the normalization property, the normalization axiom, now wherein which the probability of the whole sample space should be 1, and then an important property now which is the sigma additivity. Now, if you have events a1 a2 now which belongs to this f, okay, and then they satisfy the mutual exclusion property. Now, that means that there is nothing common between this ai and aj. So, that means that the intersection between this ai and aj is a null set which is there, and for all these events that has been considered, if that is the case, now then what we can do is the probability of union of all those considered ais which are there is equal to the sum, okay, the sum of the individual probability, and then this, now these are the three properties that needs to be satisfied. So, non-negativity, normalization and sigma additivity, and then this omega fp now which is known as famously known as the probability triplet which is there, or it is known as the probability space. Okay. And the next very important definition is the definition of conditional probability. See, as I told you, now this is a recap of things, so it will be a now what do you call a laundry list of the definitions and their properties, okay, and I will be more emphasizing on what are the conditions that needs to be what do you call taken into consideration now while applying any given formula or any given formulation, okay. So now let us look at the definition of this conditional probability, which is quite important for us. Now let B be an event, okay. Now that means that this B which is there, now this belongs to this scripted F which is there, and the probability that has been assigned is greater than 0, okay. If that is the case, okay, now both of them has to be satisfied. B has to be belonging to F, and then the probability of this event B has to be greater than 0. Now when this is the case, we define now what is known as the conditional probability of an event, of any event A. Now on B, probability of A given B, okay, so is equal to the probability of A intersection B divided by probability of B. Now to represent this A intersection B, we just write it as probability of AB divided by probability of B. Now given B, the conditional probability is a new probability assignment to any event, okay. Now we should be pretty much aware of this idea. This conditional probability which is there is a new probability that has been assigned to all the events, okay. So the notation now what we use is kind of an abuse of notation, so but we will be using it. See, once we know that it is an abuse of notation, so that is fine, at least we are aware of it, okay. So probability of B conditioned on B is 1, and probability of this is okay, sorry, there is a, this is greater than 0, okay. Now only if probability of AB is greater than 0, okay, fine. So now the new probability of each event is determined by what is common that is there with B, okay. Now you can think of it like based on the knowledge now that we already have that B has already occurred, we adjust the probabilities of all the events. Now that is why I prefer to say that, not prefer to say, that is the reason why this is the new probability assignment now which is there, okay. And the same thing can be extended for multiple events in a similar manner, okay. So now let us look into the next important definition which is there, now which is the total law of probability which is needed for us. Now let us consider a partition of the sample space. Now what do I mean by that? I have this sample space. Now let us consider that I have this B1, B2, B3 and B4, okay. Let me have this partition. Now whenever I mean partition, that between the events that has been considered, this is, that is between all these Bi and Bj for all I not equal to j, now you do not have any intersection, these are mutually exclusive things, okay. We can think of it like this. Now for an example you can think of this is B1, B2 and this is B3 and this is B4. These are the 4 partitions that are there, okay, and each of them are so they are mutually exclusive. Now in that case you consider any event A. So let's say that you have considered now this specific event A. Now this one that is there in the blue, let us consider this is A. Now what is this? Now this is this A, this whole thing is A which is there. Now how do we represent this now? Now this is union of all these 4, and each of these what do you call a slice of a pie which you can consider. Now what is common with A and B1, what is common with B, what is common with A and B2, what is common with A and B3, what is common with A and B4, you consider them and you take the union of them. See whenever we are dealing with the probability, we always consider plus and union, we normally interchange them and use it, okay. So we should be able to, and anybody who has taken a first course in probability should be very much comfortable with these kinds of notational abuse, okay. So now you have this union of AB1 till ABM, so that means that you have taken each of these section and then you have performed the union. So I can apply probability on both the sides. Now probability of A, now since now these are disjoint, these are mutually exclusive, now I can apply the idea of sigma additivity, now because of which so the probability of union which is there is sum of individual probabilities, now that will come out, and then I can apply the definition of conditional probability which is there. So and then I can write it like this, okay. Now this becomes the total probability rule or total law of probability, okay. This is a very interesting thing. So you consider each of the partition, so for whatever event that we are going ahead, so the conditional into this, the probability of the section of the partition that you are considering, okay, we can go ahead with like that. Now then comes a very important rule in probability, which is the Bayes rule. Now probability of A given B is equal to probability of AB divided by probability of B, and by the conditional probability rule we can say that this AB is this, okay. So probability of B given A into probability of A divided by probability of B, and then using the total law of probability, now we can write it in this. Now what is the partition that I have done? I have done so A and A complement. See, A and A complement are mutually exclusive, and then it is a partition on the omega. So it satisfies the need for applying the total probability law, and because of which this is how the denominator will be modified. Now this is the idea of Bayes rule, okay. Now see, it is very interesting that now sometimes now one conditional is easy to compute than another conditional. In that case, now you can use Bayes rule, and then you can interchange and do the computations, okay. So now coming to a very important notion now which is independent events which is there. Now we have two events A and B. Now whenever I say that events, so now it has to be A and B should belong to this CPRED F, that is taken into consideration, okay. So they are said to be independent, they are said to be independent if the probability of intersection of the event is same as the product of individual probabilities, okay. See, here you are dealing with the intersection, and here you are dealing with the idea of multiplication. See, you can observe that in the set space, see whatever is union and intersection, in a way they are getting corresponded with the plus and the multiplication in the probability space. It's a nice observation to make it out, okay. So now this is the definition of independence. Now because of this definition, when we use this definition in the conditional probability, now what happens is, now suppose that probability of A and probability of B, the probability of events are greater than 0 if they are independent. So the conditional probability, now you have this the probability of intersection. Now since A and B are independent, now they can be written as the products. So and then so this probability of B and probability of B will be cancelling. Now because of which, so if A and B are independent, the conditional probability and the unconditional probability will be the same, okay. So now this is a consequence of the definition. So this is because of this definition, the outcome now which is the conditional probability and the unconditional probability are being same, it is an outcome of the definition. And similarly the same thing can be applied for B given A, so you can get a similar result, and it can be easily what do you call, you can take it as a very small simple exercise that if A and B are independent, okay, now so are A and B complement, A complement and B, and A complement and B complement. All these things also will be independent. You can take it up as a nice exercise and try to prove that if A and B are independent, so are A and B complement, A complement and B, and A complement and B complement. Now the earlier definition we looked at independence of two events. Now let us look at independence of multiple events. Now if I have events A1, A2 till AM, so we define what is known as the total independence. Okay, they are said to be totally independent. Now if you take any integer k which is between 1 and m, so see what is that we are trying to say here is intuitively you take any subset of this A1 to AM. Okay. Now they have to satisfy the condition that the probability of intersection of all of them is the product of individual probabilities, that this has to be satisfied, that is what is being said here. You take any k, okay, and then that k has to satisfy that it has to be between 1 and m. So if you take k to be m plus 2 or something, now you have only m events, how can you take m plus 2 events? So it is not possible. So the condition is quite clear, and you take the indices I1, I2 till Ik. So what happens is probability of intersection of all these events is same as the probability the product of individual probabilities. Okay. Now this is what is called as the total independence. Okay. So in addition to that, we have what is known as a pairwise independence. So see there are different notions of independence, so that I am trying to bring in here. Now there is what is known as a pairwise independence. See what is being done here is, again you have events A1 till AN. Now they are said to be pairwise independent if you take any two of them. So if you take any I and j where I is not equal to j, the probability of intersection of AI and AJ is same as the product of individual probabilities. Okay. Now you take two of them, see here we are not going and putting a much more stricter notion of independence here. Okay. So events may be pairwise independent but may not be totally independent. Okay. And I leave it up to you, if it is totally independent, is it pairwise independent? Okay. Now let us look into the next idea of independence, which is what is known as the conditional independence. Events A and B are said to be conditionally independent given C. Okay. Now there has to be a conditioning event. Now the conditioning event is C if the probability of AB given C, now you can write it as probability of A given C into probability of B given C. Okay. Now when this above holds, if this is the case, now I think you will be able to easily go ahead and get this. Okay. Probability of A given BC. Now this, how do you compute this? Using the conditional probability. Now you get this. Now that you can split like this, and using the definition of conditional independence, this can be split to this, and BC which is there now can be split as a probability of B given C into probability of C, because of which this and this will get cancelled. So what remains is only this term. Okay, fine. So now events may be conditionally independent but may not be independent, conditionally independent. Okay. So one very interesting example that we take is, so if we perform independent multiple tests for confirming a disease. Okay. Now this is a very interesting example that to ponder upon, that events may be conditionally independent but may not be independent. Okay. So now it is also possible that AB are independent but are not conditionally independent given another event C. Okay. So now we should be aware of these what do you call corner cases to take it into consideration. Okay. Now these are couple of interesting properties that we should remember. So now let us go into a very interesting idea which you already been introduced during our lecture sessions, the idea of random variables. Okay. See the need of random variable, I am assume that it is clear. Okay. That means that you have to work in the space of real numbers. So you want a kind of mapping to go from our sample space to the real space. Okay. So a random variable on a probability space, now which is omega fp, which is there, is a real valued function. Okay. Now you might have already heard the famous statement. So random variable is neither random nor a variable, it is a deterministic function. So which is from omega to r. Okay, already you might have in the lecture sessions heard this famous statement. Okay, it's a deterministic function, which it's a function from omega to r. Now very interesting thing, now that is so let us say that you have head or tail like this. So x of the head you are mapping it to 1 and you are mapping tails to 0 and this is 1. See, there are other kinds of things that just couple of interesting examples that you can think of, like you go to a hotel and then what is the sample space in a hotel? Now what are the dishes that are there in the menu? So now there can be multiple mappings. So now one is each item in the menu is mapped into its rate, that is one kind of one random variable. Yeah. So there can be another random variable wherein which each item in the menu is mapped to number of calories that is there, that is another kind of random variable that is possible. Okay. See, what I am saying is there can be multiple random variables on the same probability space. Okay. That's perfectly fine. So one is you can think of billing as one random variable, and then you can think of the calories that are there in each food item that you take is another thing. Okay, fine. So now any random variable results in a new probability space. That is that you have this x, so it goes to r, b and px. Okay, this is the, see, and then please be very much comfortable about this notation which is there. This px is a new probability measure which is being because of this the random variable x. Okay. Now here r is the new sample space and this scripted b which is there is a subset of 2 per r. This is a new set of events, and this px which is there is a probability that you are being assigning, so on this space b. Okay. So now you take any event. Now how do we assign this? Now how do you assign the probability measure for these elements of this scripted b? Okay. Now this b is belongs, let us say that there is a b that belongs to r. Okay, that is a subset, sorry, that is a subset of r, and then it belongs to the event space b, and now we need to get the probability of that event b. Okay. Now how do we go ahead with that? The idea is quite simple. Now you take all the omegas that belong, all the w that belongs to this omega, now which has been mapped to this b. See, now let us say that you are going ahead and computing what is the probability of this particular element, this is in r. Okay. So now what are the w's that formed this b? You take this, and since you have this omega fp which is there and this probability has been already assigned, you take this and then that will be the probability of this b is what is being said here. Okay. Now the example that you can think of is like now in the new probability space, what is the px of now x taking the value 1. Now if 1 is here, what is 1 mapped to in the sample space? This is mapped to heads. Now this is same as this is equal to the probability of we getting the heads. Okay. Now in the hotel example that I told you, now consider that under a very restricted idea that you are allowed to take only one dish over there. Okay. Now what is the probability that your bill will be 120 rupees? Okay, you are allowed to take only one thing. So that means that, so here what is the probability of 120? You go back and see what are the dishes that has been mapped to this 120, and you take the probability of those dishes. Okay. That is how we compute the probability in the new space. Okay. So now this we write it like this, we use this x belongs to b, we just for the notational convenience we just go ahead and write this, and it is very easy to take it into consideration that okay, the new px which is there is a probability measure and it satisfies all the axioms of probability, and this is quite easy for us to intuitively understand from here, and similarly you can go ahead and prove it out. Okay. Now this is regarding the idea of random variable. See, always you should remember that. So, random variable is a function that has been mapped from omega to r, which is there. Okay, you can take any random experiment that you have in your head. Okay, good. So now let us look at couple of important functions that are involved whenever we discuss random variables. The first one being the distribution function of random variables. Now let x be a random variable on the probability space omega fp. Now we define this, the CDF, the cumulative distribution function. See, as we go along we just say distribution function. Okay, distribution function, cumulative distribution function, so we use them interchangeably. The cumulative distribution function of x is px, and please remember this. So whenever I write scripted p, now that is what I mean by a probability measure. Whenever I do not write this scripted p and then I just write it as px like this, now this is the CDF of the random variable x which is there. This is not a probability measure that is obtained because of the inducing the random variable, no. Okay, for that I write it as px like this. Okay, this is the CDF. Okay. Now the CDF is an R to R function, and how do you define it? Now for you take any x now which is there, the CDF of that x is, now you consider all the omegas, okay, now that are such that this x of omega is less than or equal to this x. See, the idea is like this. Okay, now let us say that it is an R to R function. Now let us say that you have a real line here, okay, you have got some x here. Okay, now each one of these maybe has some mapping back in the omega. Okay, now it might have a map in the sample space. Now what do? From minus infinity till this x, you add all the probabilities which are there. Okay, this is how you can intuitively think. That is why it is called as cumulation. Okay, you are accumulating the probabilities. So now here you can see this, from this notation it is very much clear that now this CDF now which is there, you can think of it like probability of for all the x now which is less than the considered value. So now if I say that, if I go into the head and tail example that is there, now let us say that this is 0 and this is 1. If someone asks me what is the CDF of 0 minus 3, okay, now before that there is no point for which a probability has been measured, so the probability has been assigned, so it is 0. Okay, now if someone asks what is the CDF at 0.5, now till 0.5 there is only one for which I have some valid probability that has been assigned. So what that is, the cumulative distribution function in that time will be the same as the probability of x taking the value of 0. Okay, now if till so from here, okay, now it will be 1. Okay. I think that will be very easy for you to now visualize now with this kind of an example. Okay, and this is very easy to see that the cumulative distribution function that you have now is completely specifying the probability assignment for this random variable x which is there. Okay. Now what do you mean by completely specifying? Now that means that if you give this CDF for all the x which has been considered, now then I can know what is the probability of each of the event. Now it is very easy for us to trace back and obtain. Okay. Now any CDF which is there should satisfy certain properties. Okay. Now what is that? Now this CDF is defined as a probability. Now any probability now which is there now for sure will be between 0 and 1. Okay. So therefore the CDF which is there has to be between 0 and 1 for all x that are considered. Okay. So and then the CDF at minus infinity is 0 and the CDF at infinity is 1, which is an extension of the same idea, and then this the CDF which is there is non-decreasing. Now see, we are not saying that it is increasing, now please be aware, we are saying that it is non-decreasing. That means that there may be some points which stays what do you call as similar to the previous point. See, the example that you can take is, for example, the CDF at 0.5 and the CDF at 0.6 will be the same whenever we are considering that what do you call the coin tossing example, where in which heads is mapped to 1 and tails is mapped to 0. Okay. Now it is non-decreasing, okay, but we should not say non-decreasing and increasing, these are two different properties. I just want you to sensitize to this idea. Okay. Now how do we say it? Now you take any x1 and x2. Now see, whenever we are taking x1 and x2, we should know that this x1 and x2 belongs to R. Okay. Now we should always remember what is this px, sorry, not this, this is an R to R function. Okay. So this x1 and x2, you take two numbers in such a way that x1 is less than or equal to x2. Okay. Now what happens is, if you consider now all x that is less than this x1, now will be this subset of this. Now because of which the probability of the CDF of x1 in the consideration will always be less than or equal to the CDF under x2 under consideration. Okay. Now this is a straightforward indication that the CDF which is there is non-decreasing. Okay. And another thing is this CDF which is there is right continuous and has left hand limits. Okay. At this point I leave it this statement as a what do you call a nice exercise for you guys. Now please go ahead and look it for now why is this needed. Now what will happen if this is not there. Okay. I leave it to you as a small exercise. Okay. Please go ahead and do that. Okay. So now this can be easily seen that if you want to measure if you want to know the probability of all the x which is in between a and b, now this can be shown that this is what is the CDF at b minus the CDF at a. Okay. Now here is the derivation for that, you can look into it. Okay. And then if you are adding this equality here, now you need to add probability at x is equal to a needs to be added. Okay. And please see the difference in the notations that I have. Okay. Now please try to understand what is it. Please be very aware of whether I am speaking of probability measure or I am speaking of CDF. So notationally now you should be pretty much clear what is that is being looked into. Okay, fine. So now post going ahead with CDF, now let us look into the idea of different kinds of random variables that we will be studying here during our discussion. Okay. The two kinds of things that we will be studying, I am not saying that these are the only two kinds of things. The two kinds of random variables that we shall be studying are discrete random variable and continuous random variable. Okay. Now there is one more kind which we shall not be looking at during our discussion. Okay. So most of the times, now 80% of the times during our course discussion we will be dealing with the continuous random variables, and fairly some time 20% of the times we will be dealing with discrete spaces. Okay. Now these are the two kinds of random variables in which we will be investing our almost throughout the course. So we will be looking at only them, and CDF is defined for all kinds of random variables. So it's not that it is only there for discrete or continuous or some other kind which I haven't defined. CDF is there for all. Okay. Now let us look into the discrete random variable. So now the discrete random variable the definition goes like this. Now consider a random variable x, okay, on a probability space now is taken into consideration from now. So a random variable x is said to be discrete if it takes only countably many discrete values. Now whenever I say countably many, now I say that either finite or countably infinite. Okay. I am assuming that the viewers of this course are pretty much comfortable with the difference between countably infinite and infinite. Okay. So yeah, okay. So any random variable defined on countable omega, now we will be countable sample space is what we are calling it as discrete random variable. Okay. A simple example is now let us say that I am tossing a coin 3 times and then that is my experiment. Now how is my random variable, how is it mapped to the R? Now how many number of heads we have obtained. So whenever I toss a coin 3 times, now either I cannot, what are the possible options, I do not get any heads, that means that when I map it into real space I will be getting 0, I can get 1 head, I can get 2 heads, I can get 3 heads. So in this case the x can only take 0, 1, 2 and 3. Okay. Now these are the only 4 values that I can obtain because of this specific mapping. Okay. Fine. Now as I told you, you perform the same experiment and then you can have a different random variable, which is how many tails are there. Okay. In that case the values, now let us say that random variable you are calling it as y, in that case what are the values that you can take, you can just go ahead and do it as a very small exercise. Okay. So now let x be a discrete random variable and it takes x1, x2 so on and so forth, and then we are assuming that now the x1 is less than x2 so on and so forth. Okay. If it not, you can rearrange and then you can always changing of names would not have any issues. Now let us say that for each of this xi we assign this qi as a probability and all these qi now will be greater than 0, and then whenever you sum them it will be 1. Okay. So now in the case of discrete points that we have, now probability of so the CDF at x and CDF at x minus will give you the probability at x. Okay. Yeah. So now this is the simple how does the CDF for the example, the discrete random variable that I have taken, I have just given here. Now till 0 it will be 0, now at 0 you will have now that means you have at 0 you will have a jump of 1 over 8. Now why is, what does 0 represents in our random space? So in our sample space it represents no head. Okay. Now that means that you get this, so you go here and then at 1 you again have a jump, and then the jump is 3 over 8. Why 3 over 8? I will leave it to you as a small exercise. At 2 again you will have a jump of 3 over 8. At 3 you will have a jump of 1 over 8 and this will be 1, it will continue like this. This is how, this is a staircase function or a step function now which is there. Okay. Now okay, so now what are the cases? One head is so head tail tail, tail head tail, tail tail head. Now these are the 3 cases which are there. Okay. Now therefore the probability at this, the jump at here this point is 3 over 8. Similarly now whenever you have 2 heads, now a similar kind of jump. Okay. Yeah. Now if you consider the cumulation of probability till that point, till 0 for x at 0, now what is the probability at 0? It you have obtained this jump, so therefore it is 1 over 8. At 1, now that means this point you would have accumulated 1 over 8 plus 3 over 8 which is 4 over 8 which is half. At 2 now you would have obtained this much 1 3 3, this is 7 over 8, and at 3 you would have accumulated the whole 1. Okay. So this is so you can see that here the CDF graph which you have obtained is a staircase function which is there, where the jump, okay, is the probability of that event happening. Okay. You can see that from this graph very comfortably. Fine. So now let us define one more, which is probability mass function, which I am writing it as small p and x like this, small p x. Now let x be a discrete random variable with x1 x2 so on and so forth. Now what is this? The PMF is defined by probability at that point. See, CDF is probability till that point, okay, whatever probability that you have accumulated till that point. So mass function is probability at that point. Now this is only defined for all the x's that our random variable can take. For all the other values, now it will be 0. Okay. So now yeah, this is what it is. Now Px is a real valued function of the real variable, so which makes sense. This is a, what is being said is this is an R to R function is what is being said here. Okay. and this is a straightforward thing that you can immediately obtain, fine. So now what is the relationship between the CDF and the PMF which is there. So now if I go till here, this is the probability at that point, this is the probability at 2, this is the probability at 1, this is the probability at 2, this is the probability at 3. So now let us say that you want the probability at, you want the CDF at this 2.5. Now how do you get it? So whatever is the valid points for which the probability is defined, you can just add them, right, okay. If you add them, that is enough, that is what is being said here. So you take i's such that the xi is less than or equal to x. So that means that if you take x is equal to 2.5, now what are the xi's that I should consider? The xi can take value 0, 1 and 2, and for each of this you add the mass at that specific points, that will become the CDF, okay. So now fine. So this PMF which is there, again this is by definition the PMS is a probability. Now this has to be greater than 0 for all x, and it is 0 for all the points in R for which the random variable is not taking any value, okay. And then whenever you sum over all the points which are there, it has to be 1, okay. This is the standard rules that has to be considered because of the definition, okay. So any function satisfying these two rules that has been stated above is a PMF of some discrete random variable, okay. So now any discrete random variable which is there can be completely specified either by giving its CDF or by giving its PMF. So if you want to understand the, now what do you mean by what do you mean by understanding a random variable? No, we want to understand that what are the elements taking, what are the probability of each of those elements occurring, okay, in the discrete case. So now either you get the CDF, so which is nothing but the sum of PMFs, or you directly give the PMF. Now given these two things, I will be able to reverse engineer and get the probability of each of the events which are there, okay. That is what is being done here, okay. So and please make note that the CDF which is there is defined for all kinds of random variables, and PMF is only defined for discrete random variable, okay. For continuous random variable you do not have the idea of PMF, okay. Now what is continuous I have not defined yet for the people of the audience, so they might be knowing it. So the PMF is only defined for a discrete random variable, okay. Now let us see some of the examples of discrete random variables. The one is the standard Bernoulli random variable, which is your tossing. One example of Bernoulli random variable is a tossing. So the outcomes, the x can have two things, two events, now success and failure, and then the PMF of the success or whatever the number for which the success has been mapped is p, and then the failure is 1 minus p, okay. And the value of p has to be between 0 and 1. Now you can think of it like 0 as the tail and 1 as the head, then you can think of this, or you can think of x is a test in which what is the probability that you perform some test and then so the person is passing in the test or failing in the test, or some disease. Now you take one bad thing that all of us remember is COVID, you perform a COVID test, and what is the probability of the success or failure, so on and so forth, okay. We can model all these experiments like that, okay. So now this is the idea of Bernoulli random variable. See, another important variation of Bernoulli random variable that we see in most of the cases is what is known as the indicator random variable. See, the idea of indicator random variable is the indicator random variable takes the value 1 if the event occurs, okay. So now consider a sample space omega fp which is there, you take a b which belongs to this event space, the indicator random variable will take the value 1 if this w belongs to b, it takes 0 if this w does not belongs to b. Now then therefore it can be immediately seen that the probability of indicator random variable taking the value 1 is probability of occurrence of b. Okay. This is what is famously known as the indicator random variable, okay, which we will be using very oftenly during our discussions. Okay. Now and then we have the binomial distribution. Now this binomial distribution which is there can be considered as n independent Bernoulli trials which are there. Now x taking the values between 0, 1 till n. Now what is the PMF? How is this PMF defined? Now it is the PMF at the point k. Now what is that you are saying? Now you can think of it like what is the probability that out of n there are k successes. Okay. So now nck into p to the power of k 1 minus p to the power of n minus k. Okay. Now where k can take the value between 0 can take the value 0, 1 so on and so forth till n. Okay. Now to completely specify the Bernoulli distribution, now we need n and p, these are the parameters. N will be a positive integer and then p will be a value between 0 and 1. So you can think like this p is the probability of heads and then out of n is how many times you want to repeat the experiment. So this is p to the power of how many this is the p is the probability of success, you want the k successes. So whenever you have k success that means that you have n minus k failures. Okay. Yeah. So now consider n independent tosses of coin whose probability of head is p. Okay. Now if x is the number of heads then x has the above binomial distribution. So this is nothing but n independent Bernoulli trials. Now we have another example is Poisson distribution. Now x here takes the value 0, 1, 2 so on and so forth and this is the PMF. So and this is the parameter, okay, we specify this with the parameter and k has to take a value 0, 1, 2 so on and so forth, and this can be immediately seen that see again any PMF which is there, now it has to satisfy certain things. Whenever we define any PMF, now you have to immediately check that whether it satisfies those conditions or not. Okay. Now what are those conditions? Now each of the PMF at each of the individual values that has been considered has to be between 0 and 1 and when you sum against all the valid values now it has to go to 1. Now it can be easily seen that now if this is the PMF, if you go ahead and sum it up over all the valid values that it can take, now it will go to 1 and similarly it can be seen for here. And in the case of indicator random variable and Bernoulli trials it is straightforward. So p plus 1 minus p, no it is 1. Okay. Yeah. And then another distribution that we will be considering is what is known as the geometric distribution. Now wherein which x takes the value 1, 2 so on and so forth with the PMF. So 1 minus p to the power of k minus 1 into p. Now what does this say is now you keep on tossing the coin till you get a head. Now that means it is asking that what is the probability that I get a head at kth instance. Okay. Now if you are getting a head at kth instance that means that all the previous k minus 1 instance you would have got the tail. Now which is 1 minus p to the power of k minus 1 into p. Okay. This is what is the geometric distribution now which is there. Okay. So now till now this is a couple of examples of discrete random variables. Now this is where we conclude these tutorials. Till now what did we see? We looked at the definition of probability, the conditional probability, the Bayes rule, the idea of independence, multiple variations of independence now which are there, and then we looked at random variables. There we specifically looked at discrete random variables. Now in the next set of tutorial now we will be going ahead and looking at the continuous random variables, different kinds of continuous random variables, and then we will be looking at things like expectations and then variance and so on and so forth. That is the plan for the next tutorial. Okay. Thank you all. I hope you enjoyed this a small section of tutorials on review of probability. Thank you. We will meet in the next tutorial.